Good morning or good afternoon, everyone. This is Mr. Steele. I'm here to deliver for you, just in case, the second lecture from Calculus AB, or AP Calculus AB at Franklin High School. In this lecture, we're going to be talking about how to evaluate limits using algebraic methods, oftentimes called algebraic limits. And we're going to look at, of course, also in addition, properties of limits, some properties that will kind of be used. We'll also look at why all these algebraic techniques that we're going to use work. And we'll do a number of examples that illustrate all of those techniques for you in their full glory, so that way you're prepared to go through and attack the problem set and understand this topic moving forward. To begin with, in our lecture, we're going to start by talking about the properties of limits. Now, these aren't properties in the sense where you need to memorize them like you might need to remember a definition and be able to recall it perfectly. They're simply properties that allow us to evaluate limits that have combinations of functions, and to simplify our work, if you will. So what's down here, and I think you'll have a piece of paper with this on it as well, that you can hold on to and use in your own notes. But basically, this is called Theorem 1.1-2. Not really, we don't really care about the name of that anymore. But these are the properties of limits. As it says on that paper, it tells you to let b and c be real numbers and let n be a positive integer, meaning something like 1, 10, 11, but not something like 1/3 or -2. And then let f and g be functions with the following limits. So the limit as x approaches c of f is L, and the limit as x approaches c of g of x is k. So two different functions, both have finite limits at a particular value, and if you recall, just because their limit exists there doesn't mean that the function value actually exists, or that the function value is in exactly the same place, because general behavior might somehow behave differently than the specific point that happens on that function. Now, with that said, understanding these properties is very quick. Basically, the moral of the story that you're going to get here as we start things off is this: limits behave nicely. And to put it smoothly, limits behave in the way we would expect them to. Basically, if you multiply a limit by or if you multiply a function by some scalar like 5, you get 5 times the limit. If you multiply what else we got there? If you add two limits together, you get the sum of the two limits. They're pretty simple. So down here, as we go and work our way through, I'm going to first just kind of write in the value. Then I'll kind of show you what it is that's really happening underneath, and we'll do some examples to kind of show you the expectations as well as kind of the mechanics of what's happening. So to start with, it says the scalar multiple rule. It tells us to evaluate the limit as x approaches c of b times f of x. And recall, b was just some real number. So we're basically multiplying the function f by b. When we do that, we basically get b times the limit of f. So BL in this case. Minus the t, and we'd have a sandwich with some tomato on it. So in here, the second property, sum or difference, we have the limit as x approaches c of f of x plus or minus g of x. Well, in that case, we're just going to add the two limits together. We'll have L plus or minus k. I'm sorry, I said add. It could have been add or subtract, depending on the situation. For product, exactly like you'd expect, if we multiply the functions f and g, their limit will be L times k. If we divide them by taking a quotient, as the quotient property shows, we end up with L divided by k. But there is one exception here. With quotients, we do have one thing to be careful of. We talked a little bit, or I assume we all talked a little bit about what happens when your denominator is 0 in the previous lecture, the first one. So you should know that in this particular situation, you do get L over k so long as k does not equal 0. In that case, you'd have to deal with some sort of undefined behavior or indeterminate behavior, depending on what it was. And then finally, with integer powers, like this is specifically for integers, although there are some other corollaries out there, with integer powers, you would get L to the n. So those are the properties, and this would be good to fill in. Like these just kind of fill out what those properties actually are. But in a sense, what I'd like you to kind of keep in mind is that really underneath, it's not so much that the property asks us to just multiply those two together. There's kind of a missing step in what's in here. So take, for instance, let's say the product property. Let's look at the product property really fast and kind of show you what's happening under the hood in that situation. So if we look at the product property, we were asked to evaluate the limit as x approaches c of f of x times g of x. So again, we're multiplying two functions together. And what we did was we skipped right to the end, and we said our answer was L times k, which is obviously correct. What these limit properties actually do, though, is they say that you can basically evaluate the limit of all the different components and pieces of your limit that you're trying to evaluate. So in particular, this expression would be equivalent to the limit as x approaches c of f of x times the limit as x approaches c of g of x. And at that point, with those two things evaluated, we could see that the first one would be equal to L, the second one would be equal to k, and therefore we would be using these properties in a very clear way to get to our answer, the guaranteed value L times K. So in truth, these two steps, like this kind of like intermediate work, isn't as necessary because this is a pretty simple thing to work with. And as we said earlier, limits behave nicely. But at the same time, it's good to see the mechanics happening. So, and more than that, it's also good to see these mechanics happening in a true problem. So here is a problem that resembles where you would apply these limit properties directly, where you'd actually think about the properties. In fact, here it is. So in this first example here, we're going to let the limit as x approaches 5 of f of x be 17, and the limit as x approaches 5 of g of x be -3. Once again, as we've said before, we don't know for sure what's happening at x equals 5 for either f or g. We just know what the general behavior is suggesting. One general behavior is approaching 17, and one general behavior is approaching -3. What actually happens at that point is irrelevant given this information. We need to know a little bit more to know that they were the same values. But as far as what we're asked to do here, we are guided then next to evaluate the limit of some combination or transformation of those functions. In this case, we're instructed to compute the value of the limit as x approaches 5 of 5f of x minus g of x over g of x squared. So in order to jump in here, like even though you could do this problem really quickly, possibly even in your head, depending on how good you are at some of this stuff, I want to illustrate what's really, again, happening under the hood. Because although you're not going to have to show this in all its depth and glory, it's good to understand why it's there, since that's the purpose of the question. So basically what I want to do is I want to apply each of these limit properties, one after another, to that expression, 5f of x minus g of x over g of x squared. So looking at this, kind of the strongest structure in here is probably that quotient. We've got something over another thing that we're evaluating the limit of. So the first thing I'm going to do is I'm going to imagine writing this as using the quotient property. We're going to have the limit as x approaches 5 of the numerator, which is 5f of x minus g of x, all divided by the limit as x approaches 5 of g of x squared. So there's our first move. We've used the quotient property in order to, break this down, decompose it into the quotient of two limits. So what is that? It's like saying that the limit of a quotient is equal to the quotient of the limits. So from there, and again, I'll change color every single time. It's fun changing colors. From there, I see a couple different things. First, in this line in the denominator, I see that we have a function to a power. And we have the power property right there as in our list. So for that denominator, so I can do this correctly, I'm going to rewrite this as the limit as x approaches 5 of g of x, and that whole limit squared, since that's really what that power property is saying. Whatever the limit's value is, we can raise it to the power. So we'll eventually be able to dig in and get our way through there. Likewise, in the numerator, I see one function, yeah, there's a scalar, but we'll deal with that in a second, minus another function. So up top, I'm going to apply a different property. I should have said this was power property. And then up top, we're going to apply the sum and difference. So we'll have the limit as x approaches 5 of 5f of x, and then we'll be subtracting the limit as x approaches 5 of g of x. Again, that was basically the difference property. So given that, we now have everything broken down save for one spot. You might have noticed it. It's basically right here. We have the limit as x approaches 5 of 5f of x, so we can actually apply the scalar property right there. So we can write this instead as 5 limit as x approaches 5 of f of x minus, well, you get the picture for the rest. I'm going to write this as quickly as I possibly can while talking at the same time. It's impressive multitasking right out of the summer, I gotta tell you. So there it is. And again, that was us using the scalar property. So given this information, now that we're here, you can see exactly what it is that we can, or how exactly we can finish this problem off. We basically are going to substitute. We're going to substitute the value of the limit as x approaches 5 of f of x, which we know right up here. Ditto for the limit as x approaches 5 of g of x. And of course, we once again have g of x's limit as x approaches 5 down below too. So we'll be able to draw those pieces directly out. And in fact, to finish this thing up, Why is Steam on? I don't know. So to finish this thing up, we can just go ahead and evaluate. So we have the limit as x approaches 5 of f of x. Right up here it says that's 17. The limit as x approaches 5 of g of x. It says right up here that that is negative 3. And then likewise, the limit as x approaches 5 of g of x is negative 3. So we're going to square it in the denominator. And then this will finish up being 85 plus 3 over 9, which is 88 over 9. Or I think it's 9 and 7/8 if you so desire to do that. 9 and 7/8, or 9 and 7/9, excuse me. So feel free to write that, but there's our answer. So now with all of this said, let me just remind you that again, what I expect to see in your work is I expect that most of you will probably just write something like this. Like the green part will be your actual, like what you show. What I hope though is as you're thinking your way through it, you'll understand what's happening in order to get us there. And in particular, you'll understand that you're applying the limit properties one by one in order to evaluate this complex function's limit as x approaches 5. The one thing I want to caution you against, I don't know how to show this in like a toxic cloud. We'll just do this over here. What I don't want in your brain, this is bad. What I don't want you to think of when you're doing this is this. And in fact, I have to strongly caution you against this, because this is incorrect. The reason being, we don't know what f of 5 and g of 5 are actually equal to. We have no idea, because again, as we talked about last week, we don't know what happens specifically at that point. We only know from the limit what the general behavior is doing. So I just caution you, encourage you to be really careful and to make sure that you realize what you're using and you don't mispresent your argument by, you'd get the right answer this way, but you'd have done it incorrectly. Because again, we don't know what's happening specifically there. We're applying limit properties, one after another, and actually after another. So there you go. So there are the properties. Again, these aren't usually hard problems, but there are some nice twist ones that you'll be able to see on your problem set tonight. And if you're curious about some of those harder versions and applications, you can look at the video solutions for those questions. Now, with that said, it's going to bring us to our actual, more principled goal for the day. We want to be able to evaluate limits when a visual picture or a table of values are either non-presented for us or inconvenient to try to produce. We want to be able to attack things algebraically. After all, we represent functions all the time algebraically. It'd be nice if we could evaluate their limits using the same techniques. So in order for us to get here, we're going to look at an example here as kind of a representative and try to think our way through what's happening. Now keep in mind, although the techniques that we're going to be doing again are not that simple, or not that complicated, they're algebraically involved, but other than that, they're pretty good. Let me again remind you that it's important for us to communicate to you and for you to understand why and how these things are actually working underneath the hood. Like what's really happening when we do these operations. So keep in mind every single time I'm going to make that a point of emphasis. So that way you take away more than just this is that thing that I do //. Like I want you to be able to understand what's happening. So we're going to begin with the limit as x approaches 5 of x squared minus 11x plus 30 over x minus 5. Now when we go to jump in here, there's something that catches my eye for the first, right before anything else. I notice that we're taking the limit as x approaches 5, and if I plug in and direct substitute 5 into my denominator, I'm going to end up getting a 0. So while that doesn't necessarily mean that the limit is indeterminate, because it could possibly be a number over 0, and this just means infinity, the presence of that 0 kind of alerts me to be really careful. And this is one of those first big communication things that we're going to look at. If our denominator is going to 0, we can't risk writing something like this. Because unfortunately, if this limit does turn out to be 0 over 0, and here's the obvious truth, it's going to, we can't say that that limit, which may have a numeric finite value, is equal to something which is not a number. Like that'd be like saying an alligator is equal to a cat. Like they're not. Otherwise, all those feline owners are going to be really surprised here pretty soon. So instead what we need to do is as soon as we see that denominator going to 0, or even the numerator going to 0, we're not going to write equal signs. We're going to show that evaluation and show that, hey, we recognize that as x approaches 5, that denominator approaches 5 minus 5, which is 0. And likewise, the numerator, which again we'll do the same way. We're looking at those two things separately, almost in a sense applying the quotient property. That numerator is going to be 5 squared minus 55 plus 30. And since that's 25 plus 30 is 55 minus 55, that's also equal to 0. So what we've just seen is that we are getting 0 over 0, but we've avoided a linkage error by saying that this limit is equal to 0 over 0, because 0 over 0 is indeterminate. So unfortunately, since this is indeterminate, we actually can't simply use direct substitution. We need something else that will allow us to open up this entire world. So from here, this is where we start to have to think a little bit. Specifically, what we're going to do is we're going to try to find some way to express this function that allows us to see what's happening around x equals 5. And the operation we're going to do is something you've done many times before. In fact, you've even done this thing before, just not in the context of a limit. Specifically, what we're going to do is we're going to look at that function, x squared minus 11x plus 30 divided by x minus 5. And we're going to think about what can we do to it? How can we transform the way it looks without, of course, violating any operations? So in here, of course, as you look at this, there's really only one thing you might be tempted to do, and that is to deal with the numerator. The numerator can actually be rewritten. Specifically, that numerator factors into x minus 6, x minus 5. And at first that might seem like an unhelpful move, since it doesn't technically evaluate anything for us. But if you'll notice, there's now a factor of x minus 5 in both the numerator and denominator. And if you think about it, the reason we got 0 over 0 was the presence of that 5. 5 minus 5 gives 0 in the numerator, and 5 minus 5 gives 0 in the denominator. If, this is all just theoretical at this point, but if we could simply divide away the x minus 5s, we'd be okay to go. But here's the problem. What we're really doing in this case is we're basically taking our expression and we're quote-unquote canceling, we're dividing away zeros. And you're not allowed to do that in general. And no, I can't deny that that's something that we haven't been allowed to do in the past. But here's the thing. In the limit, it's okay to get rid of that extra x minus 5 factor, because we don't care what happens at that one specific point. At x equals 5, anything in the world can happen, so long as the general behavior on the outside isn't affected. And in fact, if we divide away that x minus 5, we'll be left with a limit that's easy to evaluate. In fact, all we'll have left is the limit as x approaches 5 of x minus 6. And seeing as there's no denominator, we can't possibly get an indeterminate expression here. In fact, this would be equal to simply 5 minus 6, which is negative 1. And this is, in fact, the y value of the whole, which we talk about later on in the course, or in this unit. But specifically, that's our limit value. We're saying that the y values are getting closer and closer to negative 1 as the x values of this function get closer and closer to 5. If you, in fact, look at a graph of this, which I'd already pulled up on Desmos here, you'll notice something interesting too. First and foremost, as f of x, I've placed in there x squared minus 11x plus 30. And at first, you might say, well, that's weird, that rational function shouldn't be aligned, should it? And the answer would be, well, no, except those two factors divide away. Notice that we have 5 undefined on the red function f of x. Like, literally, there's a hole there, although my mouse is kind of blocking it for the moment. But basically, there is a hole there, even though we can't see it. It's just not possible for Desmos to render it. But then, if we graph x minus 6, that line, you'll notice that everything is the same, except we know here what's specifically happening at x equals 5. So in a sense, what I'm hoping you'll realize is that these two functions are exactly the same, except for one specific point. As in, they are completely the same function. They're the same person, but one has like a tiny little mole on its cheek. That's the only difference. So in other words, what we're developing is a way that we can transform a function and actually allow us to evaluate it. What we've done in this particular case, like what we successfully accomplished here, was we had, let's see if I can do this correctly, we dealt with in both cases the exact same function. The only different, I gotta do this right. What we had first was this situation. This was where we started. And then after doing that algebraic manipulation, which I mean again you'd probably just call factoring, what we were able to do was find the exact same function, except this version had that point filled in which case evaluating the limit was easy. So we use this to evaluate the limit because it was cleaner and simpler, and it was exactly the same everywhere except at one point. So what's really happening here, kind of the mechanic of what's happening, is we're finding a function that is, in general, the same as the original one, but no longer has that like prickly spot that causes all the problems. And in fact, if you wanted to see this algebraically, or written out kind of in an algebraic way, what you could do is you could think about this. The left function is our traditional one. This is what we'll call f of x equals x squared minus 11x plus 30 all over x minus 5. That's where we started. The second one, though, while also looking almost identical, save for that one point, this function is this. It's a piecewise function, which is equal to x minus 6 for all x values not equal to 5. And it's just plain old undefined when x equals 5. Now, if you think about it, we saw that there were issues when we evaluated the limit of the left one because it produced that indeterminate 0 over 0 form. This right one, though, g of x, which we know is the same everywhere, produces the same values in general. The only difference is here, we have a clearly defined general behavior that we can evaluate the limit with. So in a sense, just like we've done before, if we wanted to evaluate the limit as x approaches 5 of g of x, we know from last week that we take the general behavior. So since in general it's x minus 6, we can simply evaluate this limit as we saw, 5 minus 6, or negative 1. So in other words, this is the same work that we did before. Now this isn't something, well, there's a nice connection to last week that you could kind of infer and work your way through. In truth, there's a theorem that allows us to do this. And this is not one of the like 4 or 5 theorems that you'll need to know off the top of your head. This is just a nice theorem that confirms what it said before. So you should have this paper as well in front of you. So it says the functions that agree at all but one point, or whole theorem. So it says let's let c be a real number and let f of x equal g of x for all x in an open interval containing c. So basically this is saying that two functions are here. I'll help. This is saying that there are two functions that are identical except at x equals c. So even though we're using lines here, play along for the moment, these two functions are identical except at c. This one being f of x, this one being g of x. If the limit of g of x as x approaches c exists, which in this case we assume that it does, then the limit of f also exists and the two limits are equal to one another. So the idea is we can find a cleaner function, a simpler function, by doing a little bit of algebra. And then once you've got that simpler function, evaluate the limit using it. Because the one point that causes a problem on the original prickly one is not enough to deter us from the general behavior of the function. So again, just kind of proving why these algebraic techniques will work. Now with that said, that's a lot of time it's taken to get to this point. But now that we've seen it, we're ready to actually jump in and start to use those algebraic techniques. Now of those techniques, of course, there are a bunch. These are called the analytic or just straight up the algebraic limit techniques. And there are 4 that we're going to eventually deal with in this course, 3 of which we'll look at today. Now we just saw the first of those techniques. That first one was just simply factoring. We basically took an expression, a rational expression, or some part of a rational expression, we factored it, and we saw ways to lop off that problematic factor that was creating an indeterminate 0 over 0. So, and in fact I should even say that. This is 4 indeterminate forms. Actually, I realize there is a 5th technique. I guess I'll toss it down there. Now we won't mention it, whatever. So this is the first of 4 techniques that we'll eventually address, possibly 5, depending on how you want to look at it. Now to kind of help with this technique and analogy, I like to bring up and try to connect to some things that are out there. Like what is it that we're doing, not just like mathematically, because I think the mathematics here is clean enough, but what is it that we're doing kind of conceptually? Like what we're doing is we're transforming a function cosmetically so that it looks like something that's much easier to deal with. So as my analogy that I've been using for the last few years, I always call this trimming the quills, and here's why. Start with a porcupine, which again, maybe you've done this in your life. I know porcupines are very common pets, I'm sure. So if you start with a porcupine is a very dangerous pet to have, right? I mean, obviously, there are literal quills. They can literally get stuck in your hands. They're very painful. remember watching a movie with dogs. I think it was Homeward Bound when I was a kid, and the dog got stung by quills, and it was just in super pain because they're big old scary things. Them are sharp. Well, the truth is, a porcupine is an unsuitable pet for the average person unless you bring in a scissors. Because really the whole problem with a porcupine are the quills. So if you could just trim off the quills, you'd be left with the beautiful, cute, cuddly animal underneath. And little did many of you know, the porcupines underneath are hamsters. Go figure. Now I can hear through this computer screen in this time warp that has me delivering this lesson to you from Sunday. But as we look at this, you might question whether or not that's true. Well, to help support my cause, I have actual science. So this is the story of trimming the quills, in case you don't believe that porcupines are really hamsters. So this is a cross-curricular exploration using the scientific method. It's a thing. Oh, with biology and calculus, so you know it's real. Could have said zoology, but whatever. So the hypothesis here is that all porcupines are just hamsters that need a haircut. So I don't think you can really refute that just yet, but we're going to test this out. So there is our hypothesized equation. If you take a porcupine, cut off its quills, you get a cute little cuddly hamster. So this is an artist rendering of what we think is happening. We're taking one of those. Look at that beautifully drawn porcupine. It looks very prickly. And then it's being transformed into cute cuddly hamster. I mean, those two things look exactly the same to me, so I can't speak for you. So better rendering. Take a bunch of scissors, and oh look, hamster. And you doubted me. So the science behind it, well, it's all a bit technical, but it's there. Trust me, it's there. And the procedures themselves, of course, we'd need to acquire scissors. We need to find a porcupine, which may not be trivial, unless you go to Petco and ask for their exotic pet section, maybe. You'd have to try really hard to avoid problems like that. Then you'd just trim the quills, snip, 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 I'm sure it'd be fine. And then you'd reveal a hamster, and naturally you'd profit. That's how things go. So let's try it out. Go into the video. Yeah. Video proof. So with that said, we did it a bunch. Cuteness factor raised. Exactly. Porcupine became a suitable home pet. Oh, sorry. There's some charts. So the analysis, it happened as we predicted. Good job us. The conclusion is, yeah, a bunch of stuff. More you know. So setting aside the actual reality of the situation here, my point is to think about this process not in terms of like the nitty-gritty mathematics, although that's really nice to see the connections. It's to think about this in terms of conceptually. What we're doing is we're changing the way something looks. We're altering it cosmetically in order to make it easier for us to work with and evaluate the limit. And of course, the reasoning that works is what we just saw behind us and the theorem. So I mentioned the first technique, factoring. There are, as I said, a couple other techniques that are out there. The next one, again, these are slightly informal names, but then again, we just declared all porcupines hamsters, so I guess you can survive. So basically, the second technique we're going to do is what we'll call conjugating. This is when you multiply up and down by the conjugate. Oh, and you know what? I don't even call it conjugating. Sorry. This is easier if I just call it the more formal name. So we're going to rationalize. So our second technique is rationalizing. And rationalizing is just code for multiplying by the conjugate. So truthfully, you've done this before in pre-cal when you dealt with what are those things called? Trig identities. You were doing this in a particular form, you just didn't do it in the context of a limit. So we're going to multiply by conjugates. And again, I'll show you an example of that in just a second. The third technique does not have a fully fancy name. It's basically simplifying the complex fraction. But I usually call this common denominator ring. And that is basically simplifying the complex fraction. And a complex fraction, if it's been a little while, complex fraction is where you have one fraction on top of another fraction. So fractions in the numerator and or denominator. Finally, the fourth technique, and actually the fifth techniques are in here. I should just be honest and put them both in. The fourth technique is one we're going to hit when we come back from winter break. The fourth technique is logging both sides. Not like you go to the river and cut down trees on both embankments. We mean basically taking the natural log of both sides. There are going to be lots of situations where this works. And in fact, if you've ever been curious where the number e comes from, this would come from logging both sides as a technique. And the fifth one, the one that is the hardest for us to reach right now, is called L'Hôpital's rule. L'Hôpital's rule, sometimes written and pronounced La Hospital. L'Hopital's rule requires us to compute derivatives, which means we can't hit it yet because we haven't learned derivatives yet. We need to evaluate limits before we can do that. So just know these are all future techniques. So for us, we're going to be focusing on the first, second, and thirds. And we've already seen the first one in action. So instead, let's jump forward and look at the second one, rationalizing. So as we begin to attack this first example, as I said, using rationalizing, it's important to note why we might consider something involving rationalizing, even before we do anything else. Specifically, it's the presence of that square root. Because there's a square root, rationalizing will be a good option because the conjugate will help us get rid of that square root. Again, if that's not clear, if that phrasing feels weird, I'll show you what that looks like in just a second. For the moment, since we're being asked to evaluate a limit, I'm going to go ahead and say that our first move that we should attack is simply to check whether or not we even need to do some sort of fancy algebraic trick. Because technically, if direct substitution gives us 4 7s, we should just stop right there. So looking at my expression, as I said, we should be really careful here, especially in this lesson because obviously we need to practice the algebra, so it's probably going to be 0 over 0. If we use direct substitution, our numerator would give us 0, and our denominator would give us square root of 0 plus 1 minus 1, which is 1 minus 1, or 0. So because we have an indeterminate form in this case, that means we're going to need to trim the quills. We need to find some way to get rid of whatever's causing this prickly quill on top of this cute little hamster, so that way we can pet it and play with it, if I'm not stretching that bizarre metaphor too far. So in our case, what that's going to look like is, of course, I'm going to take my limit and I'm going to start working on that cosmetic change. Specifically, what I'm going to do is I'm going to look at what I can do to transform this so that way there's no longer any 0 and 0. So specifically though, as we mentioned, that square root in the denominator is a good candidate for rationalization. So what I'm going to do is I'm going to multiply what we'd call the conjugate, or technically rationalize the denominator. So in this case what that means is we're going to have the same exact denominator that we started with, square root of x plus 1 and 1, but in this case we're going to put the opposite sign in. So we're going to be multiplying by the conjugate of this one, because they're exactly the same binomial expressions, but one is plus, one is minus. Now, of course, if we do that in the denominator, we also have to do it in the numerator. You're not allowed to just change the denominator without also changing the numerator. So this way, in a sense, you can kind of see what we're doing is we're multiplying by the same factor. So it's just a really fancy and thoughtfully chosen version of 1. So from there, if we go to evaluate this limit, the first thing you might notice is that the numerator just doesn't clean up at all. We've in fact just cluttered that numerator up with this whole complicated radical expression. So you might start thinking that I'm that crazy person that doesn't even think about what he's doing. It's just going to do some non-useful technique that doesn't even give us anything. But here's the real reason that we did this move. It's because in the denominator, by multiplying the conjugate, what we created is what we What we created is what's called a difference of squares, something that you've been factoring for a long time in your mathematical careers. Specifically in a difference of squares, when you have a plus b times a minus b, what you end up with is a squared minus b squared. Because if you multiply, Because if you multiply that whole thing, you'll have minus at ba plus ba. Those two middle terms will zero away, and you'll be left with just a squared minus b squared. So in our particular situation here, following that very pattern, if we look at the difference of squares that we had, what we create is the square root of x plus 1 squared minus 1 squared. And simplifying those little pieces here, we're going to get x plus 1 minus 1, which equals x. So our denominator, by difference of squares, simply becomes x, which you may not have liked the numerator because it was super complicated, but that denominator is really clean. That's turned out really nicely. And in fact, there's even more than that there to celebrate. Specifically, look now. We said we had an issue because our original limit, when using direct substitution, yielded a 0 over 0 indeterminate form. Well, look, the thing causing 0 over 0 was that factor of x in both the numerator and now in the denominator. We can see what's causing it, so we can use this whole theorem in a sense. We can use this approach to divide away the x's, so that way we're finding a function that agrees at every point except for that one problematic spot. That way we can isolate the general behavior and work nicely from there. And in fact, that's exactly what we just did. this is now the limit as x approaches 0 of 21 times parentheses, and those parentheses are hugely important. If you don't use them, you will get this answer wrong. Get that over 1. And that is fantastic, because no longer is it possible for us to get an indeterminate form. If we have a 1 in the denominator, that means it can't possibly be 0. Therefore, all we have to do is use direct substitution to evaluate. And in fact, we can. We'll get 21 times the square root of 0 plus 1. Again, you can see we're just substituting here. Plus 1. That's equal to 21 times 1 plus 1, otherwise known as 21 times 2, which is naturally 42, because I work hard to make every answer 42 that I can. And so that is our rationalization technique, or our multiplying by the conjugate technique. We make things a lot worse. We can make things way worse in the beginning in order to simply clean things up afterwards. So I don't know how I could connect this to trimming a porcupine. It's like applying some sort of like Tabasco sauce thing that makes the porcupine irritable first, but then magically calms it down so you can trim the quill. Whatever. So in our case, there is the rationalization technique. So I'd say as we're looking in here, if you're someone that tends to make algebraic mistakes and you want kind of a preview of where those mistakes typically occur, the most common algebraic mistakes tend to occur first and foremost right there. People drop the parentheses in whichever one of those conjugate factors remains in the problem, and when you drop that parenthesis, suddenly your answer is different. You can even see here, if that had been dropped, this would have just been 21 times 1 plus 1 is 22. So make sure that that parenthesis sticks around. It's easy to miss. In fact, I'll even write this on there, don't miss. And then the other thing that's easy to mess up is it's also easy to mess up the multiplication of those guys. So you notice here I was super careful and even showed that step. It might be something you kind of step aside and do a little bit of work on the side for before bringing it back, or it might be something that you're just a little bit careful with. Like oftentimes in these problems, you can fix all sorts of issues if you just take it carefully and you don't rush through any sort of part of the problem. So just kind of keep that in the back of your mind. But there is the rationalization technique fully demonstrated for you. Oh, this is the exact same thing we saw before. I guess this is a definition of trimming the quills. It's using the algebraic techniques to find a function that agrees at all but one point, allowing us to evaluate the limit by direct substitution. I don't think you need to write that down because it's the same thing we've been saying. It's just written out nicely, probably for the person that needs to go online to look at the lecture, since I've never recorded this lecture before. So just something to know. Doesn't even mention logging down there, so whatever. Let's look at the other technique though. Okay. So the final one of the third of our techniques here is the one that involved, I said, finding a common denominator. And here we are presented with a classic type of these problems, which is what we call a complex fraction, because there's a fraction in the numerator of this larger fraction. So our job here to begin with is, of course, to make sure before anything else that we've done direct substitution and at least tried it. Because again, we don't want to cause a waste of time if we go through and do a whole bunch of algebraic work when our answer was staring us in the face at the beginning. So I'll start in the denominator. This will be 5 times 7 minus 35, which will be 35 minus 35, which is 0. Looks like we probably will be indeterminate. Let's see though. In the numerator, we'll have 12 over 7 minus 4, minus 4. 12 over 3 is 4, so 4 minus 4 is 0 also. We once again have an indeterminate form. That means that, of course, we're staring at a porcupine, and we are only approved to handle a hamster. So we're going to need to give this thing a haircut, clean it up a little bit, and find that function that's much cleaner, that agrees everywhere except for the one problematic spot at x equals 7. So in order to do this, again, it's going to be a little weird when you first start off. Of course, it's going to do that again. Sorry, my computer's not cooperating with me when I want to do some stuff. What we're going to do is we're going to begin by dealing with that numerator. Like basically, I think that's our first place to go through. We want to get a common denominator in the numerator so that way we have everything kind of cleaned up and we can see if there's anything that might actually factor out. So in order to do that, what I need to do is I need to make sure that both fractions or both terms in the numerator have an x minus 4 denominator. So just like we did in the past one, I'm going to multiply up and down on that 4 part by quantity x minus 4. So when I do this, of course this doesn't do a whole lot to the rest of the problem, although you might, like me, notice that the denominator itself can be cleaned up a little right off the bat, or it can be factored at least to 5 quantity x minus 7. So to start off there, I'll do that as well. And then up top, I'll notice that what I have is 12 over x minus 4 minus 4 quantity x minus 4 over x minus 4 as well. And in fact, I'm going to do two things here, and I'll use a different color to help. The first one is a algebraic move that Miss Nakamura actually showed me when I first started teaching at Franklin. This minus and this 4, like we're going to be multiplying that 4 in here, but that minus has to come along for the right also. So what I'm going to do is I'm going to change this minus into plus a negative. That way when we distribute, we can be sure to distribute that negative 4 in. And in fact, when we do that, we'll be able to do that in a second. The second move I want to make is I just want to make this just a single denominator of x minus 4. It's just going to be a little bit cleaner. So if you look in just a second and wonder why, I'm just choosing to do it now. So specifically, we'll get that entire numerator over x minus 4. That numerator is now 12 minus 4x minus a negative 16. And all of this, all this is sinking into the ocean. There we go. All of this is over 5 quantity x minus 7. So looking at that numerator, again, trying to play it a little bit careful here. 12 plus 16 is 28. So this numerator will be the same thing as 28 minus 4x. And with that in mind, I can once again factor this a little bit. Like I'm going to rewrite that version over here. I'm going to rewrite that numerator now as instead of 28 minus 4x, I'm going to factor out a GCF of negative 4. I'm going to leave it as negative 4 quantity x minus 7. So that was just me factoring it a little bit. Of course, that's over x minus 4. And our denominator is over 5 quantity x minus 7. Now at this point, other than judging me based on my poorly drawn fraction bars, we're at a crossroads as well. Like, we want to get rid of those x minus 7s, but depending on how comfortable you are algebraically, you might not see a pathway to getting rid of them just yet. Well, here's the thing. What we've really got is we've got right now a fraction, a over b, divided by something else. So if we rewrite that in a slightly different way, you'll see that this is really a over b divided by c. And when we're dividing by fractions, you might remember, that's the same thing as taking the first fraction and multiplying by the reciprocal, which means this really becomes a over bc, taking into account our little separate fraction here. So this is just how you that's how you divide fractions. So up here it's a little bit harder to see, but here's a, here's b, and here's c. Following that same algebraic pattern, or that same fraction pattern, we can rewrite this as the limit as x approaches 7 of our numerator staying the same, negative 4 quantity x minus 7, but our denominator becoming x minus 4 times 5 quantity x minus 7. And that's, of course, one way to do it. There are other ones out there. I think last year I had a student, I believe it was Carmen was the one that did it last year, that would do this to clear out that situation, would literally multiply up and down by the reciprocal. That's fine too. However you get there is fine. But there is our work simplifying things. And more important than anything else, that work we just did actually cleaned everything up for us. We now have an x minus 7 in the numerator and an x minus 7 in the denominator. And since we were getting 0 over 0 when we tried plugging in a 7 before, if we divide away the x minus 7s, we'll be left with an expression that no longer is indeterminate. Specifically, in fact, we'll have the limit as x approaches 7 of negative 4 in the numerator over 5 quantity x minus 4. And this is that function that agrees at all but one point. Function agrees at all but one point. So this is that thing we were searching for. It just is it's the exact same thing as the first function we had. The only difference is that 7, but since we want to know the general behavior, that's more than enough for us. So we can we can evaluate this by direct substitution. We'll get negative 4 over 5 quantity 7 minus 4, and that's going to simplify to negative 4/15. And again, there is our y value. There is the y coordinate of the whole for this particular function. And more importantly, we've demonstrated our ability to evaluate all these pieces. So with that said, all that's left here is to give you a chance to try it yourself. And I'm hoping my pacing has been good enough for you to actually have some time to do that. So in here, I have three functions I would love you to, or three limits, that I would love for you to evaluate. I'd love to give you a few moments here to evaluate them. So my recommendation is, if you're watching this video, I recommend that you go through and you pause the video for a few moments in just a second, and you give the class and everyone take a few minutes to go through and try to figure out what they're equal to, and then come back and I'll show the answers in the work and talk about a little bit the strategies and stuff, and you can check and then go on your merry way. So, if you haven't already, please pause the video now. Okay, since you've paused the video, now that you're back, we're going to go ahead and go through it. So again, if you haven't finished, please make sure you pause the video. We'll come right back and go over the answers. So here they are. So there were 3 answers that I got for the 3 questions. The first one was negative 13 over 2. The second one was 1/12. And the third one is negative 1 over 243. So I'd like to point out a couple little things here as you dig in. Specifically, I want to point out first a part of technique of what I did. I want you to notice that on each of the 3 problems, regardless of whether you get the right answer or not, you should show that step of direct substitution to verify. And when you show it, make sure that you're using arrows and you're not saying equals 0 over 0, because 0 over 0, by virtue of not being a number, cannot be equal to something which has numeric value. So there's the first thing to look at. The second thing that I'd be looking at is look at your limits. Did you ever make a linkage error? Did you ever say that a limit was equal to something that didn't have a limit? If you did, if say this limit was missing on this right side, then technically that would be incorrect because you still hadn't evaluated that expression. So basically make sure that your limits are used correctly or that you're not using equal signs, because again, that equal sign is a wholly mathematical symbol. From there, otherwise, you can just look at the answers themselves. As I said, negative 13 over 2, I think the first one is one of the easiest problems to work your way through. Don't see a whole lot of issue. On the second one, on part B, I think that the biggest challenge came from that 2 in front of the square root. So you might notice that I approached this one slightly differently than maybe you did. I didn't multiply by a conjugate of 2 root x plus 11 plus 8. I factored out a 2 before I started, and then I let my conjugate be the conjugate of square root of x plus 11 minus 4. That way it just cleaned things up a little bit. I just had an extra factor of 2 to carry around. It's just easy for that to cause problems. So be on the lookout if that was something that maybe happened, that could have been an issue for you as well. And again, the answer was 1/12. So moving on to the last one. The last one was pretty straightforward. The difference was here you did have to find a common denominator with both of those individual pieces. And as you worked your way through, this one was also the first one where your answer was really complex, or at least it was kind of annoying arithmetically. 27 times 9 might not be your standard thing you can multiply through on your head, or maybe you just weren't sure, or you didn't have time to actually multiply it out. Remember, this would be a fully correct final answer for this problem. If you wrote negative 1 over 27 times 9, that is A-OK. Obviously, if it was multiple choice, you'd have to find which one it's equal to, but that's slightly a different animal. So in other words, though, you do get your answer of negative 1 over 243, which is what, negative 1 over 3 to the 5th? 2? Yeah, that's kind of nice. So, with that said, you've seen all the stuff that we're going to go through in this lecture. You've seen kind of the elaborate, weird metaphor that I come up with for it, and you've kind of seen how to do how to execute the techniques with one example of each. So it's kind of a quick reminder that we started out by talking about the limit properties themselves, just these things that allow us to evaluate limits of transformations and combinations of functions. We did an example that showcased what that would actually look like formally and painstakingly mathematically, and we talked about what was an acceptable final work, in green in this case, and what you shouldn't be doing, which was in that pink brain over on the right side. Second, we did an example, or we kind of explored things using an example that required the factoring technique. We saw that we could divide away a factor that causes 0 over 0 and everything's fine. And the reason was because the function that's produced is exactly the same except at that one specific point. And since limits describe general behavior, it doesn't matter that there's one point that's different. No one point can change the value of a limit. So in this case, we're able to evaluate with the simpler function, which comes from something called the whole theorem, or the functions that agree at all but one point theorem, which just kind of formalizes this technique we're doing. Extending forward and using that technique a little bit, we talked about the different options we have to algebraically evaluate, and in a sense what that means is find the function that agrees everywhere but one point, and we connected it to the story of the porcupine, or the ballad of the porcupine, who is just a cute little cuddly hamster who has really long, spiky, sharp, dangerous hair. So we went through that, we looked at examples of each, both the rationalization method, which is kind of cued in by the square root's presence, and multiplying up and down by the conjugate kind of works your way through. And then we also looked at the common denominator one, which neutralizes complex fractions and lets us find that factor that's hidden inside that's causing an indeterminate form. Finally, you tried a couple problems, and we went over the answers. So with that said, without further ado, that is the end of our lecture. Hopefully this has been informative and helpful, useful to you, and hopefully you feel comfortable giving this a shot. So you'll be working on the problem set titled Algebraic Limits tonight, and as always, for the harder problems and for some of these things that you might want to see another example of, feel free to take a look at the video solutions and see if those help you work your way through some of that stuff. Without further ado, I'm Mr. Steele. Have a great day, great afternoon, great evening. Just, yeah, be good. Bye.